Begin now. Welcome everyone to the Ontology Summit. Today is the 3rd of June, 2026, and we are absolutely thrilled to have John Sowa, who will be speaking today on neurosymbolic AI to check and correct LLMs. John is a fellow of Permian, and he is a longtime member of the Ontolog Forum and the Ontology Summit, and he's a member of the Ontolog Board of Trustees. So welcome, John. Go ahead.
Okay, what I'll start with are the issues about semantics of language and thought, and what are the problems of converting them to a form that everybody can understand and the computers can understand and process directly. Now, large language models have proved to be extremely valuable for language, but language maps a continuum of sensations to a finite vocabulary. And the human languages are derived from everything that people think and talk and see and hear and do. But thinking is based on perception, action, feelings, and plans. And the problem is that our computers don't know that. All they see when they're processing large language models is written language, and the language does not have all of the sensation. It's isolated from perception, feelings, actions, and reactions of everybody. And the question is, how much of a human intelligence is lost in a mapping to the LLMs? Now, the large language models are remarkably similar to a joke back in 1900 where there was a cartoon where people dump books into a machine, turn a crank, and expect a stream of knowledge to flow through the wires. Now, that was a joke in 1900 about what the year 2000 would be like. And amazingly, that joke turned out to be true. Now, the problem is that the LLM methods are excellent for many purposes. For machine translation from one language to another, they are superb. They totally outrank anything that has ever done before. They're useful for searching texts, but they are unable to guarantee that the results they produce are absolutely correct. And there's one example where a lawyer used them in a legal case, and it generated an imaginary precedent, created a citation that seemed to be legitimate, but the opposing lawyer found out that this was absolutely false. And the problem is that there is no test, no way for knowing that what these LLMs discover happens to be correct. And that is the fundamental principle. So anything that generated by LLMs is basically a hypothesis. It's a best guess. And if it's inconsistent with the ontology or a verified database, it might be rejected as false. But if we don't have any other knowledge, we just don't know whether what the LLMs generate are correct. Now, in industry, the ontologies are necessary for accuracy and precision. In banks, you must have absolute precision in the final result to a fraction of a cent. However, during the intermediate computation, they might have multiple precision arithmetic so that the intermediate results may be much more precise than a single cent. And with each business, you have different problems and different issues. And the problem is that mistakes can be costly. They can cause bankruptcy of your company or deaths to humans. And 99% certainty is unacceptable. Nobody's going to fly in an airplane that crashes 1 out of 100 times. It's just not possible, not desirable, certainly, and it's not acceptable. Now, this diagram shows a cartoon where the man on the right has asked a question, And the policeman has this precise mental model of exactly what roads to take to get to the desired goal. But his explanation is just going across a bunch of words, and the man on the right has the idea on that you go straight to the stoplight and then you do something, but it's just a jumble of a jumble. And that is the problem with language. It's not ideal for thinking or communicating spatial patterns. And it's not good if we're talking about emotions or a huge number of things that people need. And here's an example of an egg yolk diagram that was used by Lehman and Cohn to classify objects. And so here we have a question of the word chair. And in the egg yolk, you have uh, things that everybody consider to be chairs. And there are a variety of different kinds of chairs, but all of the things in the yolk are exact chairs. The ones in the egg white are things that differ from a chair in many ways. There's a folding chair, a rocker chair, a wheelchair. These things are not chairs. And then on the borderline, you have a toilet, which you can sit on as a chair, so it can be used as one, but it really has other functions that are more important. And then you have things on the outside, like a footstool or some stairways. You can sit on them as a chair, but they're not chairs. And that is the problem that you have in language. We use the same words for a wide range of things, and we use the same thoughts for many similar kinds of things, but we can't get our computers to do what humans do. And here's another example of what is a number. The original numbers were integers starting with a 1. And then the Chinese indeed invented a zero, and that immediately created a huge extension. And then other people created fractions and the value pi, which is an infinite number of digits for precision, and things like square root of 2 has an infinite number, but you can compute it better. Then you have things like imaginary numbers, and you have things on the borderline like infinitesimals and quaternions. All of these things are numbers in some sense, and the word number just keeps going farther and farther away. And these are, you talk about mathematicians as being precise, but for a mathematician, the word number by itself includes so many things that you can never be certain what any particular book is talking about. And then you have the microsenses. The linguist Alan Cruz coined the word microsense for the huge number of variations. And you have examples in cooking. You have methods of frying, baking, and slicing that vary with the ingredients, but every ethnic has a totally different way of doing the cooking and the available utensils and methods and spices and everything. There is no such thing as a precise term for any of these meanings. And then file system, Unix, Apple, Microsoft, IBM, they all have very different definitions for what a file is. There's no fixed set of meanings that can adequately describe a continuous, dynamically changing world. The question is, how do you find the correct microsense? And for example, suppose you hear the sentence, "My dog bit the visitor's ear." Now, from the knowledge of dogs, you would know that it's probably more likely to be a large dog like a Doberman rather than a small dog like a Dachshund. But if the visitor was in the habit of bending over to pet a dog, it could even be a Chihuahua. And then you also have an ambiguous parse. The chicken is ready to eat. Well, you normally assume that the chicken is food and it was cooked and prepared as for a meal. But if you say the dog is ready to eat, you would assume that the dog was begging for food. However, there are different cultures where people make different assumptions, and the dog made on the menu. Now, Zelig Harris, who was Chomsky's thesis advisor, invented the term transformational grammar, but he emphasized that language understanding requires empathy. And Chomsky got rid of that term and he tried to make it very formal. But the point is that our natural language includes and must include empathy, and LLMs do not have empathy. Now, empathy depends on feelings. And Damasio and Carvalho said that feelings are mental experiences that depend on the body states. They signify physiological need, tissue injury, and so on. And the neural substrates can be found at all levels in the nervous system, all the way through many, many different parts of the brain, including parts of the brain that are beneath the nucleus and even in the cerebellum. And the question is, Damasio said, I'm ready to give the very teeny brain of an insect, provided it has the possibility of representing its body states, the possibility of having feelings. And then he says, what flies don't have is all the intellect that and the feelings, and they cannot, and they are not tied in with language. Now, the question is, what do we do? Now, the issue of visualization is important, that mental models are more fundamental than language or logic. They're the meanings that express in language are based on perception, and perception involves an immense amount of detail, far and away beyond anything we could express in ordinary language. And the notations of mathematics and logic are abstractions from the symbols and patterns of language, and that's even worse. Now, computers can manipulate symbols faster than a human, but they are much less efficient in perception and action. And that makes them unable to process language the way people do. So how could computers support human-like methods? And some people claim that these LLMs are somehow going to be replacing humans, but they can't even begin to touch a tiny fraction of what humans do and think. So that's the major problem. Now, intelligence uh, indicates many things, implies many things. All animals, including humans, are born with some kind of tools. But birds can't wash dishes for the same reason that humans can't wash dishes with a sewing machine. They are using the wrong tools. The tools of a bird are superb for many things that humans cannot do without very complicated tools, but birds can do them very easily. And the point is that humans can make elaborate tools, but there are many kinds of species that have a huge number of different kinds of tools. Birds have an instinct to build nests, beavers build dams, and humans speak language. But the details depend on the animal's built-in tools, and that is now language is a mental tool, but it's only one of a huge range of mental tools that we have. Now, in mathematics, the mathematician said that mathematics is never deductive in its creation. The mathematician at work makes vague guesses, visualizes broad generalizations, and jumps to unwarranted conclusions. So mathematicians do not do precise thinking, especially at the very beginning. It's only at the final stage that when the mathematician becomes convinced of the truth before he can write down a logical proof, the deductive stage of writing the results down and writing a rigorous proof are relatively trivial. In other words, writing the proof is trivial compared to discovering it, and discovering it does not depend on this rigorous method. And Einstein, who was basically a physicist, but also a powerful mathematician, said that the words of language do not seem to play any role in my mechanism of thought. The psychical entities which seem to serve as elements in thought are signs that are more or less clear, and the elements in my case are visual and some of muscular types. How do you convert muscular thoughts into a precise mathematical form? That is a very serious question. So, Damasio, the neuroscientist, said, oh wait, no, that's Yeah, they said that the um, yeah that the when brains make maps, they are creating images, the main currency of our minds. Ultimately, consciousness allows us to experience maps as images, and the maps and images form mental models of the real world or the imaginary worlds in our hopes, fears, plans, and desires. Words and phrases of language can be generated from them, and they provide a model theoretic semantics for language. But the problem is that the words may define the criteria for truth, but the underlying thinking methods are flexible, dynamic, and situated in the daily drama of life. And LLMs are certainly not flexible, dynamic, and situated in the drama of life. Now, ontology, as the topic of our subject that we deal with in this ontolog forum, that ontology specifies models of the world. So on the left, we see a picture of the world. And on the right, we have a formal theory about some aspect of the world. And in the middle is a model, which can be some graphic representation of some kind. And that model is an approximation to the world. And the model may have a precise denotation, uh, which is exactly the same as the denotation of the theory. So the approximation is good, fair, poor, and the denotation is true or false. Now, the problem is that engineers have this saying, all models are wrong, but some are useful. Different people for different reasons may specify different ontologies for the same parts of the world. And the results derived by the LLMs must be tested against whatever ontology is intended for whatever purpose. And that's a major question. Now, we also have to consider the neurocognitive cycles of what goes on in the brain that includes the neurons and their relationship to cognition. And the point is that all learning is based on patterns of perception and purposeful action. And by trial and error, people extend their beliefs to make better predictions about the world. So the observations derive propositions from images, and then we have induction, which derives general propositions from multiple examples, and then we have a mixture of images and propositions, and you could call that knowledge soup, the whole bunch of everything you put together. Now, abduction selects a proposition to form a hypothesis, a theory. Analogies may relabel a theory of one topic and apply it to another. Deductions from a theory generate predictions, and actions test the predictions against reality. And effects of the actions lead to new observations, and frequently used perception action patterns become habits. And overlord responses are computed by the cerebellum, not by uh, the huge cerebrum, but by the cerebellum, which actually has more neurons. The cerebellum, in some sense, is more powerful in its processing power than the huge cerebrum. And that is a very serious question of how do you deal with it. Now, Charles Sanders Peirce distinguished three formal kinds of reasoning, and he used the terms deduction and induction had been used for years, but he coined the new term abduction. And abduction consists in examining a mass of facts and allowing these facts to suggest a theory. And then the second kind is deduction or necessary reasoning. And he made the point that deduction is certain, but only for ideal objects, for these abstractions. So deduction is performed on these abstractions that are many levels removed from what we actually experience. And then the third way of reasoning is induction or experimental research. And induction is very critical. That's what translates this huge mass of stuff in the world into what we are thinking and computing and representing in language. And only the end result, what goes into language, is the only thing that LLMs process. So they're not processing this immense amount of other thinking and reasoning. Now, here's a picture that shows that that's Charles Peirce in the middle, and it shows the cycle, the cognitive cycle of pragmatism. And we start with what's in our brain, in cognitive memory. So in any kind of thinking process, by abduction, which can be extracting, guessing, or adapting, we choose some theory. It may be a new theory that we just made, or it may be an old theory that we pick up and start using it. And in any case, we may have to revise the theory to adapt it to the current situation. And then by deduction, we make some prediction, and then by action, we test that prediction against the world by some experiment or just observation of some kind. And then after the testing, then we take what new knowledge we have gained, and by induction, we add it to our cognitive memory. And so this cycle is a logic of pragmatism that occurs in every branch of science and also in everyday life. We're constantly using this kind of constant reasoning, and what what is done in science is just a cleaned up and professional method. But even the scientists themselves, in their initial stages, are doing the same kind of tentative guessing that humans do. And then the implementation, we can use some kind of a computer processing method where we use for the total knowledge that's in the human brain, we represent that by a kind of knowledge soup. What's in our brain is not totally organized. Some of it is. Some of the things that we learned in math and science may be very precisely organized, but most of it is just a very vague sort of way. And by abduction, you select that can be knowledge discovery, statistical methods, data mining, analogies. We select some piece that's relevant to our current problem. And by belief revision, we might revise it. And then by deduction, there are various planning systems, inference engines, theorem provers, and analogies. By deduction, we make a prediction, and then we test that prediction by stimulus response, CAN procedures, perception action cycles, analogies. By our action, we test it against the world, and then by induction, which can be by neural nets, Bayesian nets, pattern recognition, analogies, whatever, we add it to the knowledge soup. And that is a diagram of the human methods mapped into some sort of a computable kind of way. Let's see. Oh, yeah. Okay. Now, John Boyd discovered a similar kind of loop, which he called the OODA loop for observe, orient, decide, and act. And the first two steps involve in the brain, they involve the occipital lobes and the parietal and temporal lobes. And the next two steps, decide and act, involve the frontal lobes for reasoning and motor action. And these four steps and their associated brain areas in the observed stage, the observed visual input goes to the primary visual cortex, the occipital lobes, but object recognition and naming involve the temporal lobes much deeper. The orienting arrives the parietal lobes, relate vision, touch, and sound in cognitive maps. Then there's the decision stage, which involves the frontal lobes, but other areas store the knowledge soup and the mental models. And then finally we act, and the action schemata are patterns in the premotor cortex of the frontal lobes. So in emergencies, each step of this loop may be traversed in a fraction of a second, but in more complex thinking, these steps might take minutes, hours, or days when we're really doing complex reasoning. And that is John Boyd's OODA loop is very similar to the cycle of pragmatism that is based on Charles Peirce. And now there's another issue. John Boyd originally designed his OODA loops for uh, guiding airplane pilots, but he later extended it for guiding consulting and industry. And Graves and Garrett, two more followers who were working on complex problems in engineering, they were using these OODA loops to analyze and solve what they called wicked engineering problems. And wicked problems are the things we encounter every day. Wicked problems, as they say, involve complex interdependencies between systems that involved, and incomplete, inconsistent information about the problem context. Wicked problems are dynamic and span many domains with complex legal, ethical, and societal aspects. Wicked problems are the kind of things we meet every day of our lives. We don't see these nice, neat little things that are processed by these LLMs. We see very, very complicated interdependencies. Now, the LLMs can discover those complex interdependencies that happen to be documented in a huge volume of information on the World Wide Web. But the problem is they don't apply that to any problem that we're doing. Just look out the window at the immense complexity in the world, and there's an open-ended, an infinite number of possible applications, and the ones that are documented in in the web are just a tiny fraction. And the point is that LLMs cannot discover solutions to truly wicked problems because they wouldn't be wicked if they had been solved. And as a summary about these issues, the question is, how do we get to AGI, the people who claim that we will that the human brain has already been surpassed by these computer things, and it is true that they work on the with AGI and the other kinds of things could come up with a huge amount of information faster than people can. We can ask a question to Google or Claude or any of these others, and they come up with answers in just a few seconds that any human being would take a long time to study, analyze, research, and finally write in that elegant sort of way. But the point is that they are just limited to that finite part. Now, Zelig-Harris, that the teacher, who was the thesis advisor for Chomsky, made the point that we understand what other people say through empathy. And George Burns made a joke about it. He said, sincerity is everything. Once you can fake that, you got it made. But the point is, George was making a joke. But could his point be true? Empathy and sincerity depend on feelings. AI systems do not have feelings. Could they fake them? Is it possible to have some way where our AI systems can fake them? Well, it's certainly not going to be through LLMs. They don't do that kind of thing. Now, hardcore programmers claim that feelings are irrelevant, but feelings are essential for all living things, from a bacteria, from a fly. They all need it. Its feelings are a protection against danger. They are a guide to food, health, better living conditions, and they promote cooperation and avoidance of conflict with other people. They are the basis for aesthetics, ethics, and empathy. And the question is, are feelings necessary for AGI? And what can we do? Is it possible? Well, that's basically my part of the talk. And next, Arun Majumdar will continue, and we'll have a question and answering session after Arun is finished. So can we now transition to Arun? Who's making the transition?
Sorry, I was trying to fiddle with the buttons here. And I'm just going to get very pragmatic about a few things. So let me share my screen.
Can you stop sharing?
Let's see here. How do I do this? Share, replace.
John has to
I think
stop
this
sharing
one
first.
does it. Is this it? Let's see here. Share. Can you see my screen? It should just be a
Yes.
command line. Okay. Um, so what I'd like to do is I don't know if this is sharing my screen or sharing your screen sharing. Okay, so let me do a test and see if the test will work. And we'll know very quickly. Well, that didn't show up. Let me try it again. Okay, let me try this. I'll stop and I'll come right back. Just bear with me while I try this one more time. It was only sharing one window and I wanted to share my screen, not only one window. So let me try this. This should hopefully work. Share. And I want my whole entire screen. Now I should be able to switch and I should be able to put this here. And I guess you can see my screen now with a folder and a terminal in the background. Is
Yes.
okay, great, thank you.
Yes.
All right, so I'm going to talk about a typical day in the life, which is going to be the journey of an analyst and a briefer. And what I'd like to do is give you a real world example of the kind of work Permion does. So this is going to be more of a demonstration and talk through that applies the concepts that John has been talking about. At the high level, we take neural engines, LLMs, we package them into Permion compiled formats. I'm going to demonstrate that for you. They're very, very fast and you can do many things with them, but ultimately they are abduction machines. They're not truth-telling machines. So they create hypotheses and proposals. And then there is a mapping between the surface form and logic. And we use conceptual graphs and we use ontologies. These ontologies come from things like FrameNet, Charles Fillmore's resource. They come from the CSLI verb ontology, which John and I worked on and built. It's an ontology of verbs based on Beth Levin's categories. And we also use, higher level ontologies like the Dublin Core and others. So this is a neurosymbolic system. So that's the first thing I want to say. It's a neurosymbolic system. So if I look at one of these files, I have 100 HTML documents, and each one of these, is it has all kinds of news to it, right? Official transcripts and what happened in April 2024, et cetera, et cetera. So I will get out of Safari. So each of these is a different source document. Now, if I run my basic, so I'll do X infer, and we'll do some more examples. This is going to load our engine. Whoops, I didn't want that to happen. Let me kill it. I'm going to just kill it and ls_.md open prompt. I want to show you a prompt and get rid of that and get rid of that. And I don't need the notes here. So this prompt, which hopefully you can sort of read, and I don't need that there. This is old garbage. Oh, I see it keeps, don't want the search bar. All right, well, I'll give up on the search bar. I'm not sure why it's, let's try this. Okay, there we go. All right, sorry about that. So the instruction is to collect 25 plain text file references out of a set of hundreds of downloaded documents. So the first problem is which of those documents is relevant, and how do we then rank those documents? So we use a graph-based method, which is sort of a loosely based method using page ranking of documents. This is something Paul Terrell, my late colleague who passed away, wrote about, and he's one of the most cited authors for text rank, which is what the algorithm is called. And you can very quickly rank a set of documents based on interests. So we use that algorithm from Paul to do that selection process. The second part of this prompt is to pretend to be something. So it says here, role and objective. You're a strategic analyst for the Department of War. Your objective is to create a threat assessment report for specific military installation, operation, or exercise based on publicly available open source information. It goes on to say the report will be used to brief senior military officers and non-technical government officials. The task is to generate this threat report for the Republic of the Philippine Islands. Specifically interested in the exercise called Balikatan and some focus areas, Luzon, Cebu, Mindanao, Palawan. Audience and tone. So assume the report is for a congressional staffer or senior leader with no technical background. Tone, maintain a neutral, professional, objective tone. That's a very emotion-laden statement. As John was saying, everything has emotion to it. But here we're trying to, counter what could be overuse of adjectives and adverbs in the generation process. And then there is the statement of work, which is the required threat vectors and structure. So the report must be structured using the following 5 threat vectors. So we have to identify aerial threats, cyber threats, subsurface threats, and land-based threats. And then there's something about formatting, citations, and how that needs to appear. So let's now go to our actual. So it's going to launch the engine, and we'll do some more examples after this. So that's the prompt. It's now reading all the files. And you may not have caught it at the beginning, but it did load a model. And it's now processing. So what's going on and what's different about this? Well, the first thing that's different about this is it runs on my MacBook Pro. There are no GPUs on this MacBook. This is an Apple M1 Mac from the year 2021. I have 64 gigabytes of RAM, and I'm running Sequoia 15.7. And we can always get more information on my MacBook. I'm running an Apple M1 Max, and I have 64 gigabytes of RAM. So this is, by all intents and purposes, a vanilla off-the-shelf computer, nothing special. But the second difference is we're not using RAG. Okay, RAG, which is called Retrieval Augmented Generation, uses sort of a keyword search engine to pick out some documents and then process them. What we're doing is looking at every single document using the graph-based text ranking algorithm to subselect based on our interests, and then using LLMs and our internal logic to read at high speed and process every single piece of data. So we're not missing a thing. So let me just give you a little example. Our evaluation rate on this laptop has hit 9,385 tokens a second. And our performance in generation has hit 204 tokens per second. And we'll just let it continue. And as you can see, it's going through the land-based threats, surface-based threats for every category. It's figured out what's important. This engine was developed by Permion. When you look at the way LLMs are managed, they use something called a chat template. Those chat templates have a grammar, which is colloquially known as a generative BNF or GBNF. And the chat templates are run using regular expressions. What we did is we transformed that into an extended definite clause grammar using object-oriented prologue, because that's what our engine is built with. And object-oriented prologue allows us not only to represent arbitrarily complex grammars, but to also provide variables in those grammars that can have semantic restrictions. That's much more powerful than regular expression-based parsing, because now you can parse chunks of knowledge, chunks of data. You can convert them from the textual form to their semantic forms. Here's now where it has ended. So it's synthesizing the final report. Okay. And here is the briefing that it's generated. We'll just read a little bit of it. We won't do the whole thing because I've got other things to show you about what John had been talking about. But I do want to say three very important things since this is an international audience. The first thing I want to say is that Permion was awarded the first place to represent the US as the winning company in the G7 Government AI Grand Challenge competition. So we are the winners of that competition here in the US, and we represent the United States for that prize. The problem set that we tackled was very similar to this one. It was to analyze many different, you could say, cross-risk geopolitical documents, and then build policy-based guidance around that. That's a very complex, wicked problem, as John had mentioned. And the videos of Permion's G7 winning capability, which is called the Digital Subject Matter Expert. It's an application that runs in AWS and runs also in the AWS Top Secret Classified Cloud. So there are two AWS instances. So if you're a government officer, you can go to the AWS classified intelligence market and get the capability there. Otherwise, it's behind a paywall, obviously, on AWS. But this brief that was generated starts with a statement about the briefing that really echoes what was requested. It provides the context, so official statements, exercise reporting, historical records. It also provides a little bit about what it's been asked to do, which is identify different threats. And so here's an example: aerial and airspace related risks. Public reporting in this corpus points most clearly to airspace related pressure in northern Luzon. We can go to the next line and see that unsafe air encounters, okay, in Scarborough Shoal west of Luzon. And you get some sources, which came from what was downloaded, okay, those HTMLs that we talked about. And it goes on to cover every other category. And so let me just uh, load. I'm going to load some more things. So I'm going to load some models here. Whoops, models. But I'm going to load some of our agents. So here are 12. Um, and hopefully this will all load. Yes, it's loading. And you can ask a question like, why is ontology important for data semantics, right? This is a very vague question. Oops. Now you know it's real software. It just crashed. Um, so this is definitely, there's no fake software. We don't use fake software. Let me do this and let me try again. Just do it like this. I'll just run let me try this like this, X. Okay. And hopefully I can just load it again. And I'll actually do this. Multi-prompt. So what I'm doing is I'm saying I want to talk to all the agents. I want verbose. And I'm going to ask my question. And now it's going to answer the question. Okay? Again, the speed here is quite fast. And what's valuable about this, if an agent cannot answer effectively, it will not give you a useless hallucinated answer. Okay. And what this really demonstrates is that LLMs are used to propose hypotheses and produce candidate abductions about what something could mean. And the logic engine allows you to have policy controlled generation of what the engine provides. And under the hood, of course, we have these definite clause grammars. We're able to provide chunks so that LLMs don't have to try to manage a whole lot. And I clearly have something going on in my machine because it did generate, but I have and I don't know if it's because it's Zoom, but this is the first time that's happening to me. So I'm going to call this the demonstration proximity effect. Spooky action at a distance. I'm not sure what's going on here, but that's very strange. Okay, we're going to stop here. I will try one last thing, which is to say help about help. So if you were to get this engine, you could have all the different types of help. And you would also have the ability to train and tune your models using logic guided refinement. That's very powerful because it means instead of taking months or years to tune a model, a year and a half sometimes, the logic guided version will synthesize correct things very, very rapidly and allow a semi-analytic process to tune your model. So you actually go very, very fast. There are some unique things that we have, like disk streaming technology. So you can run models. If you have 1,000 different LLMs that you've downloaded from Hugging Face, as long as you have a fast SSD, you can run all of those models right from the disk streaming engine. So that's quite unique. And then, of course, there's all of the um, uh, uh, prologue and logic capability. There's compliance to ISO 24707 common logic. So what I'm going to do is just stop here so I don't get another crash. but I will get out of share mode and I'll take any questions that John and I can take if there are any.
Oh, Aaron, there was some questions about whether you're using some packages that are available commercially, and the point is that what the Permion technology is all built based on the work by Permion, and it's much, much more precise than anything that's available. And if you notice, if you ask Google a question, they will take a little bit of time before they produce their answer, and they're using this immense system that is gobbling up an immense amount of power, an immense amount of water to cool this engine, and you're running everything on a laptop. And on one laptop, you take that text that came in, analyze the whole text, and then produce this reasoning method, producing a huge amount of output, all on just one laptop. No water cooling, no immense amount of space. It just fits on your table. That's it. That's important to emphasize.
Ian, I think the point about that is privacy and sovereignty. The other important element is you can take this with you anywhere and work on your own materials without exposing it to anyone. And because it runs on a laptop, and I was running, by the way, 12 LLM models there simultaneously. You can obviously this serves agentic AI very strongly. You can do a lot of things. Thanks. Any other questions? Oh, we allow you to load any foundation models you wish. Thank you, Gary, for asking that question. So anything that's on Hugging Face or any other, there's a few other places that you can download models. Three important elements. One, you can download a model. If it's too big for your computer, you can run it using our disk stream technology. Obviously, it will run slower because you're bounded by the SSD, but we do very clever things. One of the clever things we do is we can stream the tensors that need to be computed from the disk. So we do a pre-index over your model. When you ask a question, it picks which parts of the model are going to get activated. So that's a prediction part of our technology. It takes those predicted tensors and with a few extra ones too, it throws them into a RAM buffer, and then it runs the calculation using our core evaluation engine. So we do not use Llama, VLLM, LM Notebook, Ollama. There are lots of open source engines available. This is a proprietary engine. Yes, in fact, thank you, Marcia, for asking that. The G7 Government AI Grand Challenge shows the knowledge graph side of this, illustrates it, it's fully visual, and it shows how we can actually learn an ontology. We call them proto-ontologies. So if you have a base ontology, you can learn a proto-ontology from a domain and then refine it with human input, because there's always things that are tacit or implicit knowledge that's not available in the source material that a human being as an expert will have in their heads. And so you want to be able to have that human in and on the loop. Great question.
Well, Aaron, one thing you can emphasize is that we do not use any kind of a standard ontology that people use. We can use any ontology anyone has developed for any purpose, and we can design new ontologies automatically from a given set of data. So you can have a
Sure.
special purpose ontology for your application automatically generated on the fly for what you're doing right this minute.
Exactly. There's a lot of power in the engine, and there's a composite way that the system can learn. The system can save what it's learned to an external database, and so that way you don't have to do the learning again. Yes, Gary, the answer is indeed. We have common logic. So we support common logic implemented in Prolog LogTalk. That's a fully object-oriented logic programming language, and it makes the representation and computation with common logic nice and easy, and you can generate controlled natural language from it, or you could generate languages that autonomous agents can use. So common logic is very important. And then we provide a range of different types of modal reasoning so that you're not restricted to one type of reasoning, but the exchange, the denotational exchange of data itself is done with common logic. Great question. Thank you for that.
Any other questions? Gary,
I do have another question. How are emotions, as discussed by John, evident in this implementation? The importance of emotions was made.
Yeah, so the part of that prompt that said, conduct a neutral tone. There are so many emotional models. Like there's the Johnson-Laird model. There's a lot. There are models with four emotions. Joy, anger, hate, and fear. There are emotional models with seven emotions that include words like disgust or revulsion. Um, so I can't comment on which emotional model would be most appropriate, but I can tell you that emotional models are used in stock trading. They have different forms of emotional models because you try to use vector spaces to learn uh, the uh, the model, the human model structure, and so obviously you need markup for things like news, markup for things like Twitter messaging, so you can capture a baseline, for example, in a stock market situation. But the model that you use, that's the choice of the implementer. So we provide the apparatus to implement the models, but we don't make the choice of which model is appropriate for which purpose. Does that help?
Oh, Aaron, also you can mention that your system handles an open-ended variety of different natural languages. So you're not just limited to English. You can
Sure. Yeah.
even you can have cases where people even switch languages in the middle of a sentence, and the system will automatically detect that. So can you mention what languages are supported?
Yeah, so there's certainly what's called simplified Chinese. There's Chinese, Mandarin, Russian, German, French, English, Arabic, uh, and a lot of these depend also on models that are native language trained, as well as the ontologies that come from, example, International WordNet, right, or the multi-WordNet collection. And then those are threaded together through the synsemantic IDs, so that ontology structure is always available. For example, Russian WordNet can be connected with Chinese WordNet. They both exist, right? And you can have English WordNet. And so now you have, the sort of higher level ontology because WordNet doesn't produce the domain ontologies. It gives you just a very high level ontology. And you can add to that with additional resources. Um, and this is very important because when you're dealing with generative LLMs, you want to be able to establish some baseline of what you accept as ground truth. Um, it's very hard to accept uh, LLMs as a truth generator. It's very easy to accept them as a hypothesis generator. And so as long as you have a logical process that you can use to govern behaviors, policies by which generation is accomplished validation of both inputs and outputs to alert the human if there's an overwhelming amount of ambiguity, right? To reduce that. So there's many purposes, but yeah, we all of these are resources that are available in the open source or public domain. As I mentioned, we build the runtime programming language full stack AI engine to support these elements.
Yes, and one example was the translation from Chinese to English that you were able to do competitive to the best human translation, and it was impossible to detect which translations were done by Permian and which translations were done by professional humans.
Yeah,
That's
for that it was multiple models, so it wasn't one. Again, sometimes there isn't a one size fits all, and you have to have a multi-agentic structure to do that. The demonstration I provided earlier, running 12 generative agents, is just the tip of the iceberg of what you would be able to do, because now you could take all of their outputs, right? And you could synthesize based on re-ranking the content, semantic alignment, which you can do with a semantic distance measure, the logic checking and validation. So there are lots and lots of things. No two LLMs necessarily generate the same output. And so I would encourage anyone to work with multiple models to achieve better than vanilla results. So that's the conclusion. Yeah, more is better, but with control. If you have more and you don't have control, well, then it's a free for all, and that can be very confusing.
Oh, there was a question.
There are a couple of questions in the chat.
Oh, okay. Could someone
Something about
ask them for me?
Yeah, one of the question was about abductive agents, and the fact is the whole system is abductive. It does abduction, deduction, induction on every step of the way.
Yeah.
So there's no such thing as an abductive agent. The whole system is abductive constantly.
Yeah, so there's a virtuous cycle, and you can call that the Persis pragmatic cycle of reasoning that John has written about extensively, where abduction proposes candidates, and then you can use theory revision. So theories will license the appropriate candidates, and you can test your candidates using deduction. And then for the gaps that may exist, you use induction to learn further to then regenerate abductions again. So it's sort of a cycle where these things work together. What is abduced versus what is deduced versus what is induced. And then you have human input, obviously. You have to have input from the world, which is either data sets or human beings. Is there another question that there is, John? You said a couple of questions on the chat.
Another question about conceptual graphs.
Sure. What's the question?
Can you demo the use of conceptual graphs?
Yes. So we do. And so on the G7 demonstrator that's online, that uses conceptual graphs.
Yes, in fact, conceptual graphs are what our system was started with when we had the old VivaMind system 20 years ago. And the conceptual graphs are the standard representation internally for everything, and any language. So there are multiple languages that can be processed, and including the option of monitoring conversations where people are switching from one language to another within a single sentence. And the Permian system handles that without it perfectly fine.
So Aaron and John, this is Gary again. I do have a question and maybe an idea for improving the demo.
Yeah.
It seemed to me that you have the three types of logic or reasoning, and then the fourth one is the whole thing together,
Yep.
including the abductive, deductive, and inductive. For a demonstration to connect to John's presentation, if you ask the system to show the workflow, the outputs of each stage, it would sort of help connect what John was talking about and show how the system is actually working.
That's a great idea. Thank you. We as implementers, we sometimes have too many hyperlinks in our own brains, and we forget about the perspective of the listener or the viewer. So I'll update the demo so that there is I'll call it a walkthrough version that will say, okay, let's have a very simple example. And I think that would fit. Thank you for that.
Great.
Can I throw in a question about emotions?
Sure.
This is Tom. My understanding is, or the way I read John's part, that emotions is like important in the decision-making process. But it sounds to me like you're applying emotions on the prompting rather than the reading of the data. Is that correct, or?
That's partly correct. So the prompt request for a neutral tone, as I say, can come with a model, right? And models measure emotional content of utterances. That's what generally happens. And I mentioned the most popular use of it is in stock market trading, where people use sentiment analysis. And there's a lot of examples of how this runs. For example, there is a Sentinet, which is a sentiment word net, and it has a set of categories of words, and then there are other resources that use phrases. And again, these are human generated, human marked up, and then they are machine augmented. So you end up with an interpretation of being able to say, well, this is this emotion that's present is fear, or it's joy, or it's anger. And so if you detect above a threshold and you set the threshold that there's too much emotion in a phrase, you can send it back to the engine to regenerate. So that would be the use of a sentiment detector for neutralizing overly sentimental statements. In this particular demo that I just showed, all we did is leave it at the prompt level. In more complex work that we do, we use lots of different models, including sentiment. But I don't, one of our partners is working on a psychologist's assistant. And so the recorded transcript of patient and psychologist goes to a text stream, and then this text stream is machine marked up for alerts to the psychologist to review, right? So it saves them time in the process of assessing a best regime for a patient. And that particular person, obviously a trained expert, I have no trained expertise in clinical psychology, but they had a very particular way of how they made the assessments. And so we encoded those in Prolog rules and vectors. Does that help, Tom?
Yeah, that's a good application of it. So that would be basically analyzing, let's say, some AI input and detect whether there's some mental instability or some other like weird questions that might be asked and flag it.
Yeah.
I was just my first thought was if I want to make a scientific decision or like a fact, learn a fact and put it into a graph, I don't really want emotions in it because they'll just screw the problem. So that's where my question came from originally.
You may want to put the fact in the graph, but you may want to attach a co-reference
Yeah,
to an
I was just
annotation that
thinking
said the utterance carried
questionable.
this fact with, anger or with fear or, because that could be useful, right?
Yeah, right. Okay, cool.
Any other questions?
Yeah, I agree with Gary. I think for what people call agentic AI, there's a big distinction between virtualized abstract machine entities and embodiment. Um, and in physical, we'll call it physically embodied AI, where AI is attached to every sensor, to I will call it a kind of um, it requires an entirely different structural representation to build a model because you have to actually have a physical AI working in the physical world. So the AI has to do what basically a child does, is learn to walk, learn to grasp, learn to, that's all stuff. And there are folks that are building these in synthetic environments, where the AI is learning from the physics of its environment, but that's still a physically embodied modeling system. But it's a great point. Thank you, Gary.
Yeah. And I think one important point to emphasize is that all of this is running on a computer laptop on your table. And you don't need a huge engine with millions of NVIDIA chips. It's all running there. And you're doing the LLMs, you're processing LLMs, you're processing language, multiple languages. You can handle streams in which there are multiple people talking multiple languages and handle them all and mapping them all into the same kind of logic representation. And the logic representation is full common logic represented in conceptual graphs. So you have full language understanding. You don't have just some very tiny little thing like these owl things, which is just an insignificant subset of this immense amount of processing. And it's all being done, as you can see, it's all being done in real time and processing a large amount of text and producing a huge amount of output just while you're waiting. That's far better than
I could make one statement that I think will be useful to this group, and I will, if you allow me, when you get Permion's technology, you get a full handbook with all of the different elements, including how it was built, how it was the architecture, the programming reference. We are building an AI chip because the technology was written to be at a level that it can compile directly to silicon. There's the large graph models and the sort of path to AGI. We're not there, but there's a section on agentic AI and agent spaces. There's the programmer's guide, the XVM log talk reference, which speaks about log talk and then the data types and its customized version, which runs within XVM. So, and then you have a master index. So if you're interested in, narrative domain examples or, dialogue protocols, you can just directly go to the agentic programming handbook. So this is a full stack system that we have built over the last decade. I hope that helps for what it's worth.
Aaron, I also did have this question I put in chat on whether you have any plans to connect to an application like Mathematica or mathematical computations,
Oh,
therefore handling different models.
well, you're hitting our secret agenda, which is to connect to all these things. This is actually a very exciting type of development. Obviously, companies like Mathematica have extreme and deep domain expertise. The core engine of Mathematica is absolutely compatible with the core engine of XVM, which is the X virtual machine based on X machine theory. So from a logic interchange, interoperability, integration standpoint, it's very easy to imagine a future where XVM agents are working with Mathematica for, I'll call it, mathematical discovery sciences, where you're exploring new branches of mathematics. And I think, Terence Tao has some YouTube videos. There's a few people that have YouTube videos who are, prize-winning mathematicians that are working with AI and excited to move it forward beyond the current associative limits that it has. Great point. So if Dr. Wolfram is out there somewhere listening to this, yeah, feel free to reach out.
Unless there are any other questions, it seems like a good point to conclude. So thanks to John and Aaron. That was a very insightful talk, actually two talks. And thanks also to all of the participants who have asked some very insightful questions. And with that, we will adjourn the summit.